So, we were doing a particular problem. We had this square loop, edge length A and current I going in this loop, and this is in xy plane, and away from this, quite far away from this loop, we have a point xyz, and we want to write the magnetic vector potential there. So, started with I direction, x direction, AB and CD, they are in x direction. So, we write this AB where the current is I. For our mathematical calculations, we treat this as a linear charge density, so that you have a charge I times A on this AB. So, on this AB, the linear charge density is I. Total current, if you see, this will be, or total charge that is assumed to be here is I times A, and similarly minus I times A, because we have to take x component of this current element dl, and the dl is in this direction, and therefore the x component is negative. So, we have this situation, and we would like to have, this is our origin, this is x axis, this is y axis, and then there is a point xyz, and we would like to write the electric potential because of this charge on AB and CD at this point xyz. And for that we made this preparation, that this charge IA here and minus IA here, that makes a dipole, and the dipole, for dipole, if you have dipole moment P, so this is the direction of dipole moment, and the point where you want the your potential is here P, and if this OP is making angle theta with the direction of dipole moment, then here the potential is given by 1 over 4 pi epsilon naught magnitude of dipole moment P cos of this angle theta and divided by r square. So, this is established result from electrostatics, and we want to utilize it. So, this can be treated as an electric dipole because this point is far away. What is the dipole moment? If you use this or this, then the dipole moment here will be this charge IA and times A, and the direction will be this direction, negative to positive, so minus j cap. That is the dipole moment of this, right. You can use this or you can use this, and then this whole charge I times A somewhere here you can put, and this IA here you can put, and this separation is A. So, it is like minus IA here plus IA here, minus q plus q makes a dipole, and the dipole moment is charge multiplied by the separation. So, IA square and negative to positive, so it is in minus j cap direction. So, this is the direction of P, this is the direction of P, and here is this point capital P. This is that point where we need that field, and therefore, this is theta, right. This theta is the angle between that origin to or dipole to the point P, this is r vector, and dipole moment is here, and the angle between them is theta. So, here the dipole moment is this way, and that origin to that P, this line is here, this is your r vector, and therefore, this is theta. This theta you will be writing the potential. The potential will be 1 by 4 pi epsilon naught, then P is I A square. So, the magnitude is I A square, and then cos theta, cos of this angle, this thing is r, and here it will be r square, this r square, now cos theta. So, if you take this angle here, and this is r, and this will be pi minus theta. So, what is this r cos of pi minus theta? If you drop the perpendicular here on the y axis, this angle is 90 degree. So, you have a right angle triangle here, this is r into cos of this angle, that will be this y, that will be this y. So, r into, say r into cos of pi minus theta, this is actually y, this is actually y, the y coordinate. What is y coordinate? From the point drop a perpendicular on the y axis, then whatever is the length from the origin, distance from the origin, that is y, that is the definition of y. X coordinate, y coordinate, z coordinate. For x coordinate you drop a perpendicular on the x axis, for z coordinate you drop a perpendicular on the z axis. So, this is y, and this y is this r times cos of this, that is pi minus theta, and therefore, you have cos theta here, multiply by r here and multiply by r here, and for this r cos theta, this is now minus r cos theta, which is y, and therefore, r cos theta is minus y, and so this is equal to minus this minus r cos theta is minus y, so minus y here. So, minus I a square and then y, and divided by 4 pi epsilon naught here and r cube here. So, with these two currents which are along the x axis, positive here and negative here, with these two currents here, if I want to write Ax, the x component of vector potential. So, using these two, we have, assuming that these are charge densities, we have written the electric potential, and therefore, it is very easy now to write what is Ax. Ax is obtained just by replacing this 1 by epsilon naught by mu naught. So, mu naught by pi minus mu naught by 4 pi. So, this 4 pi is there, and 1 by epsilon naught we have written there mu naught, I a square y, I a square and then y, and divided by r cube, that is Ax. Now, it is vector potential because of the current in these two lines. Now, what is the current, what is the potential due to the other two lines? BC here, this is BC, this is BC, and the current is this way, and correspondingly here you have dA, and the current is this way, this is D and this is A. So, these currents are along the y axis, positive and negative. So, because of this, if you want to write the this vector potential, by the way, it is only Ax, you do not have any charge or any current here in y direction and no current here in z direction, no current here in y direction or z direction. We have chosen only these two which are along the x axis, and therefore, for these two only Ax will come, Ay will be 0, Az will be 0. Now, come now in this case it is in y direction only. So, there is no current in x direction, there is no current in z direction. So, for these two Ax and Az will be 0, and I will only be writing Ay. So, here is the origin, and if I write corresponding mentally, I treat them as charge distribution with linear charge density I. This is positive direction. So, plus charge here, how much? I times A. I is the linear charge density and A is this length, therefore, I times A is here, and this is in the negative y direction. So, this will be negative charge here, once again this Ia, magnitude is Ia, and this is the origin, this is x axis, this is y axis, x y z is somewhere here. This is again a dipole. If this x y z point P is far away, again this will be a dipole, and the dipole moment, this dipole moment will be I into A, that is the charge, minus q here plus q here. So, charge and then multiplied by the distance, this distance between the two, and that is A. So, it is I A square, dipole moment, electric dipole moment, and the direction is negative charge to positive charge. So, this is the direction. So, it will be in x direction. So, I cap, that is P. And because of this charge distribution, because of this assumed charge distribution, because of this dipole that is here, what is the electric potential at P? And our equation is this. What is cos theta now? What is cos theta now? Cos theta is the angle between the dipole moment and this r vector. Here, this is the r vector. This is origin, and I need this vector potential here. So, this is r vector, and the dipole moment is along the x axis. This is the dipole moment in this direction. So, this angle is theta. This angle is theta. So, if I write V, V will be 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, and then here P cos theta. So, P is I A square, P is I A square, cos theta, this is theta, cos theta, cos theta, multiply by r here and multiply by r here. So, this r square, I am writing r cube, so that I can write r cos theta here, and this is r, this is theta. So, r cos theta is this length from here to here, r cos theta. Drop a perpendicular, and then this is r, this is theta. So, this will be r cos theta, but this is nothing but the x coordinate. That is how the x coordinate is defined. Drop the perpendicular on the x axis and see where is the foot of perpendicular from the origin. So, that is x. So, this r cos theta is just x, and hence you can write this as I A square divided by 4 pi epsilon naught r cube and then x here. That is it. It is all in y direction, no current here in x direction or z direction. So, this gives you the vector potential in y direction only, and therefore, it is giving me A y. My total vector potential that I need is because of all these four, all these four. So, these two I am taking together, that gives me A x, and these two will give me A y. So, A y is equal to A y, 1 by epsilon naught is written as mu naught. So, mu naught by 4 pi, mu naught by 4 pi, and r to the power 3 r cube here, I times a square. So, I times a square here and x, and Az is 0. There is no current in z direction, and therefore, Az is 0. That is it, Az is 0. We have obtained the vector potential. A is equal to mu naught I A square by 4 pi r cube, and then we have y in x direction. So, y minus y in x direction and plus x in y direction, x j cap. This is our answer. Alright, so this is how the vector potential can be calculated once the current is given to you. We had done two examples, one was surface current in x direction, another is this current loop, square current loop in xy plane. So, create this equivalent electrostatic problem, write the potential, electric potential, and that same expression you rewrite with 1 by epsilon naught replaced by mu naught, and you get this A. Now, if you want magnetic field at this point because of this current loop, if you want the magnetic field here because of this current loop, you can take curl of this. So, that is also possible. B at P, that will be curl of A, this A that we have just calculated. Now, if you write it in this fashion and try to use that curl which we had been doing, I j k del del x del del y del del z and then a x a y a z, it will be a difficult task in the sense that this a x is having y divided by r cube, and r cube also contains x y z. So, this has to be inside. So, you will be writing here mu naught I a square divided by 4 pi, that can be taken out and can be written here, and for a x you will be writing minus y by r cube. So, for a x you will be writing minus y divided by r cube, and that is x square plus y square plus z square, and then 3 by 2. Similarly, a y, all these things are common, and after that x divided by r cube. So, for this a y you will write x divided by x square plus y square plus z square and then 3 by 2, and a z is of course 0. So, you can do it, you can write the magnetic field, and if you take I cap, it will be del del y of 0, that is 0, and minus del del z of this. So, that z is there, you have to take care of that. Similarly, if you write that j component, then it will be this del del x of 0 and del z of this, and if you write k component, then it will be del x of this quantity, del y of this quantity. So, it will be little more complicated, but still you can do it and get this magnetic field. The other way of doing it is, we will keep this I cap and j cap intact. We will rewrite this as A is equal to mu naught I a square over 4 pi r cube, and then use spherical polar coordinates r, theta, phi. To remind you what is this spherical polar coordinates, we have x, y, z axis as usual. Let us take this as z, this as y, this is x, and then you have some point. The coordinates are, first coordinate is r, distance from the origin, that is r, and if you write a unit vector in this direction, that will be r cap. R increasing direction in which just r is increased, that is r cap. And then if you drop a perpendicular from this point on the xy plane, now you have to make your imaginations. This x axis is coming this way, this x axis is coming out of the board like this, and this is that xy plane, and this point can be anywhere, not necessarily in the plane of the board. So, from there you drop a perpendicular on the xy plane. So, let us say it falls here, join from the origin, and from x axis what is the angle of this line, that is known as phi. In this phi is same as the phi in our cylindrical coordinate, essentially. This is z axis, and if you draw a circle here, z with this z axis as the axis, then this is phi cap direction. Here this is phi cap direction. here this is phi cap direction, 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 and so on. So phi cap direction is same as that we were using in cylindrical polar coordinates s, phi, z. And the third one, so phi direction is here and this is here, and the third one is theta direction. This angle is known as theta. With the z axis, the angle made by this OP with the z axis is called theta, and without changing phi, without changing r, change this theta to theta plus d theta. So you will be going in this direction, right? In this plane, it is this theta is becoming theta plus d theta. So you are going this way. This is theta cap direction. So these are spherical polar coordinates, and you can work out that z will be equal to r cos theta. Very clear, very clear. This is r, this is theta. So z, r cos theta will be this z. Make a perpendicular here, and that is z. So z is r cos theta, and in this plane, this will be r sin theta. R cos theta here and r sin theta here. The resultant is r. So this is this. And x component will be this cos phi, this multiplied by cos phi. So x coordinate will be r sin theta and cos phi, and y coordinate will be r sin theta sin phi, r sin theta and then sin phi. We have done a detail in our classical electromagnetism 1 chapter, but just to revise, these are the coordinates. So you can use this and this, x and y. For x and y you can use this. So this a vector is minus y I cap, minus y I cap. So minus, and what is y? Y is r sin theta sin phi, r sin theta sin phi I cap, plus x j cap. X is r sin theta cos phi, and then j cap. So you can take sin theta out, you can take this r also out, and you can cancel it here. So it is now mu naught I a square divided by 4 pi r square. So I am cancelling this r and this r with one of the r here. So r square, and sin theta we can take common out, and then you have this minus sin phi I cap and plus cos phi j cap. And if you work out what is this sin phi cos phi I cap j cap, this combination, it is all in xy plane. It is all in xy plane. So we can make a diagram in xy plane itself. Let us say this circle I am trying to draw. So this is our x direction and this is our y direction. This circle we are trying to write here. Origin may be somewhere else, but on this line itself. So it is parallel to the x direction, it is parallel to the y direction. And then this is your phi cap direction. This is your phi cap direction. And if you work out very simple, what is this cos phi j cap? Remember, this is phi, this is phi. So perpendicular to this and perpendicular to this. So this angle here is phi. This angle is here is phi. So if we can work out what is this cos of phi and then j cap, and minus the other component is here. So minus sin phi I cap, that is phi cap. So this thing is phi cap. So this is simple mu naught I a square by 4 pi a square, and then this is sine theta and this is phi cap. So, if you transform it in spherical polar coordinates, then this a vector here becomes just this thing, this one. Now, if you do curl of A and use the spherical polar coordinates. So, let me write the expression for the curl of a vector function, right. So, for a spherical coordinate, curl of A is equal to 1 by r sin theta, 1 by r sin theta here, and then del theta sin theta a theta, sin theta a theta. Never try to remember these things, right. Never try to cram all these long expressions. Whenever need arises, consult the book. So, del theta of sin theta a theta, sin theta a phi, this is a phi, sin theta a phi, and then minus del a theta and del phi. This is with r cap direction, right. So, there are 3 terms. This is r cap term, which is 1 by r sin theta, and then del theta of sin theta a phi, and minus del a theta del phi. Then the other term is 1 over r here, and then 1 by sin theta here, 1 by sin theta here, and del a r del phi, del a r del phi, and minus del r, minus del r, and then r a phi, r a phi, and that is theta cap. Okay, 1 by r, 1 by sin theta, del a r del phi, and then minus del r of r a phi theta cap, and finally you have 1 by r here and del r here, and r a theta, this is r a theta, and then minus del theta of a r. Long expression r theta phi. So, this is phi cap. Okay, so that is the expression. Now, in our case, our a vector is this. So, first thing is that only phi component is there. So, a r is 0, a theta is 0, and a phi is this mu naught I a square, and then divided by 4 pi, and this is r square, not a square. So, this is r square here, and this is sin theta here. So, sin theta over r square. So, that is a phi, that is phi component, it is this. So, since a r and a theta are 0, this a theta is 0, I do not need this term, this goes to 0. A phi is not 0, a phi is not 0, so this will remain here, and then a r is 0, so this term goes away. Here a phi is there and del r is there, so yes, this term will be there. Here it is a theta is 0, so this term is not there, and a r is 0, so this term is also not there. So, what is left? So, what is left? 1 by r sin theta, 1 by r sin theta, and then bracket del del theta of what? Sin theta into a phi. Here is a phi, here is a phi. So that actually this will be constant. You can write outside also, or you can write here also. So mu naught I a square divided by 4 pi, this is anyway constant, and then sin theta by r square. So sin theta over r square. So I have written which term? 1 by r sin theta, del theta, and then sin theta into a phi. So a phi is sin theta, so this will be sin square theta here. Okay, and then the other surviving term is here. So plus 1 by r, or minus, this minus I can write. So minus 1 by r, and then we have del del r. This is minus 1 by r, and then del del r of what? Of r into a phi. A phi is here mu naught I a square by 4 pi, and then sin theta over r square, right. So one term surviving here, and that is 1 over r sin theta. So 1 over r sin theta, del del theta of sin theta. So sin theta I have multiplied here, and a phi is mu naught I a square 4 pi and sin theta by r square. Other surviving term is here minus 1 by r into del del r here. So this r here, and then just a phi there. So a phi is mu naught I a square 4 pi sin theta by r square. It is 1 over r sin theta here, and then this mu naught times I a square by 4 pi. This will be anyway common, but nevertheless this r square is also I can write here. Why? Because I have to differentiate with respect to theta, partial differentiation. So r will be treated as constant, and then that sin square theta. So it is 2 sin theta cos theta. Then minus 1 by r, and now it is del by del r. So differentiation with respect to r, theta will be constant. So this sin theta will remain as such. So it will be mu naught I a square by 4 pi, this 4 pi, this is r here, this is 1 by r square here. We will write that, but first sin theta, and then del del r of what? Del del r of 1 by r. So this is 1 by r. That is all we have to do, and this is of course minus 1 by r square. So you can write that as minus 1 by r square, minus 1 by r square. So you simplify this, and I am writing the final result. This will be mu naught times I a square, which is the magnetic moment magnitude, divided by 4 pi r cube, and then 2 cos theta here, 2 cos theta r cap, and plus sin theta theta cap. And this is a very useful equation. This I into a square is remember it was square. So a square is the area of that loop, and current into that area is magnetic dipole moment. So this is dipole moment. You can write this as m. So for a current loop, the magnetic field at any point far away from the loop is given by this, if we are using proper spherical coordinates. So this formula is very useful. I quite often use this and such need arises frequently. So, that is all for this.